study of moist air. So we're going to talk about ideal gas mixtures. We can then solve some open system, closed system problems where you have a gas mixture instead of a single component fluid. And then the study of moist air and psychrometrics. So the forms of the ideal gas equation. This is the form you probably remember. PV is equal to NR bar T. True? You know each term in there? Pressure, absolute. Volume, N, number of moles, typically in kilomoles. R bar, the universal gas constant, 8.314 kilopascal meter cubed divided by kilomole Kelvin. True? And T must be an absolute. So the temperature and the pressure must be absolute pressures. If you take and you divide by the N, you get V bar. That's another form of that equation. True? PV bar is equal to R bar T. What is this V bar right here? That's the specific volume on a molar basis. It's how many meters cubed per kilomole. Then if you move over to a mass basis, you have PV is equal to, I'll do it in two steps, N R bar T, but you multiply by the molar mass and you divide by the molar mass. When you multiply by this, you get M mass. And so this equation is PV is equal to M and then RT. True? Where R is R bar divided by the molar mass. That's a kind of bad looking R bar divided by the molar mass. So you can get the R for air, R for CO2, R for water vapor. Okay. And then you can also divide both sides by M. You get PV is equal to RT, where this is now the specific volume on a mass basis. And one last equation that's is useful is P is equal to rho RT. What did you do? Well, a lot of people like mass density, which is the reciprocal of the specific volume. So you just introduce mass density. So these are common forms. I'd say this is probably the most common form of the gas equation. This probably is the second most and the third most and maybe the fourth most, and not to be the least common form, but so there's 5 different forms of the ideal gas equation. We need to be good at going back and forth between them. We also have the molar analysis and then a gravimetric analysis. This is the term for a mass basis. So on a molar basis, you can have an analysis of a gas mixture, or on a mass basis, you can have an analysis of the mixture. Probably the best way to think about this is you need to go back and forth between molar, number of moles, and mass, M. How do you do that? If you multiply by cap M, the molar mass, you get this equation. True? Is that how you jump back and forth? And you're very good at using the molar mass. So let's say whenever I solve a problem like this, I encourage you to set it up in a table. Think about the component. Think about the molar mass in kilograms per kilomole. Think about the amount maybe in kilomoles. The order of the table isn't as important as the information in the table. Y is a mole fraction. So I is the number of moles of the species or component I divided by the total number of moles. Sometimes we'll put a TOT for total. Sometimes just leave it off. N without a subscript be the total number of moles in that gas mixture. And then maybe over here, mass in kilograms. And then the last one, mass fraction. So on a molar basis, you talk about the mole fraction, Y. On a mass basis, you talk about the mass fraction. The mass fraction for component I is the mass of that component divided by the total mass in the mixture. So you just have to make up maybe to work through this back and forth. But if you had nitrogen, maybe oxygen, maybe the molar mass of nitrogen, 28, 32. Maybe you said that it was 3 moles and 4 moles. Then if you did the sum, there would be 7 moles, true? Guess what Y would be? 3/7 and 4/7. True? See how we do that? And then what is the mass if I had 3 kilomoles of nitrogen? It's 3 times 28. That gives me how many? That's times 28. And 4 times 32. And then if you sum that up, you get the total amount of mass. And then to get the mass fraction, it would be the 3 times the 28 divided by that sum of the mass. And 4 times 32 divided by the sum of the mass. True? So you can go between mole fraction and mass fraction. Use a table. Use a table. I use a table. It helps organize the information. Dalton's law of partial pressures. So let me just read this. A mixture of several ideal gases will exert upon the walls of a container a total pressure equal to the sum of the pressures exerted by each of the constituents as if they were alone in the container at the same temperature as the mixture. So in your thought process, have a container and just fill it with maybe so much of this purple colored gas and so much of this red colored gas. True? Maybe the purple is oxygen and the red is nitrogen. And think about the pressure that is exerted total on the walls of the container. Then in your thought process, have an equal size container and an equal size container. So the same volume and the same temperature. But in the first container, only have the red. What did I say the red was? Maybe the oxygen. And then in the second container, only have the purple. What was that? Maybe the nitrogen, right? And you'll find that this pressure is less than the total, and that this pressure is less than the total. But when you add them up, they equal the total pressure. That's the concept of Dalton's law of partial pressures. How many people are familiar with Dalton's law of partial pressures? So what you can do is you can maybe step through it a little more systematically. If I had the total number of moles, that's equal to the number of moles of A plus the number of moles of B. That makes sense, true? And then if I said, what is if I use the ideal gas equation, the ideal gas equation would be N is equal to PV divided by R bar T. Is that true? PV is equal divided by R bar T is equal to N for the ideal gas equation. So what we could say is the total N is equal to pressure total times volume divided by R bar T. And then over here, A behaves as an ideal gas, the same volume, same temperature. So you have the pressure exhibited by A times V over R bar T plus pressure at B, V over R bar T. Each of these equations have the same V over R bar T, so they cancel. And we're left with just saying something. This is a truthful statement. And it follows then that if all of them behave as ideal gases, then the total pressure is equal to the sum of the partial pressures of the gases. One other thing to be aware of is that, let's say I write down this equation for the partial pressure at A using ideal gas equation is the number of moles of A, R bar T divided by B. True? That's another expression of the ideal gas equation. And if I take that and I divide by the total pressure, here, let me write another equation. P total is equal to N total R bar T over V. True? Okay. So take this equation and divide the left-hand side by P total and the right-hand side by P total, but instead of P total, put N total R bar T over V. These cancel. And what we're left with is this ratio right here. Number of moles of A divided by the number of moles total. What is that? Is that Y sub A? Is that the mole fraction? Yeah. So the mole fraction is equal to the partial pressure of A divided by the total pressure, or another way of writing it is, if I wanted a quick expression for the partial pressure of A, the partial pressure of A is equal to the mole fraction for that species A times the total gas pressure. Look good? Great. Good review of chemistry? Good. Ready to solve a problem? The molar analysis of a gas mixture is 40% nitrogen, 50% CO2, and 10% methane. Given a temperature and pressure of that gas mixture, determine the mixture molar mass. Then determine the analysis in terms of a mass fractions. Then determine the partial pressure of each component, and then determine, et cetera, okay? So we'll take it one step at a time. What's the recommended practice when you have these mixtures like this? Use a table. Use a table, true? And so in the table, come in and create a column. What I'm going to do is let you write down some of this information, then I'm going to do it in Excel because it's just so much easier for me. And it's cleaner. You can see it, okay? All right? And then if I need to, I'll remind myself of the values. But take a look at that information, and then I'll jump into Excel and solve this, okay? Ready to go in Excel? So what we do in Excel is I would just make a table like this, a component. So what components do we have? We have nitrogen, we have carbon dioxide, I misspelled that, CO2, and we have methane, true. And might as well put molar mass in units of kilograms per kilomole because the molar mass does have units. It's 28.01, it's 44.01, and 16.04. Now, in this problem, they gave us the mole fractions on a mole basis. Let me clean up this table a little bit. Make it centered, make it bold, maybe increase the width there. There we go. So it's 40%, and it's 50% of carbon dioxide and 10% methane. That's just our mixture. Now, what I like to do is I'm trying to get over toward mass fraction. I want the average or the molar mass of this mixture. So I'll assume that there's 1 kilomole total of the gas. If there's 1 kilomole total of the gas and the mole fraction is 40% of nitrogen, how many moles or kilomoles of nitrogen are there? This almost seems too silly, 0.4. So I'm assuming that the sum here is 1, and lo and behold, it is 1. So let me try and repeat that. They gave me Y. I'll assume that there's 1 total kilomole of the gas. Hence, I know that there's 0.4 kilomoles of nitrogen, 0.5 of CO2, and 0.1 of CH4. Now that I know how many moles there are, what is the mass in kilogram of 0.4 kilomoles of nitrogen? Is it that? Sure. And so it's 11.204. I'll just drag that down. So I have 11 kilograms of nitrogen, 22 kilograms of CO2, and 1.6 kilogram of methane. If I sum that up, what does that tell me? The total mass of a mixture. Now, if I come down here and I say, what is the parent molar mass of the mixture? You know, something like that, M of the mixture. Okay, would it be the amount in kilograms divided by the amount in kilomoles? And would that give me the units of kilograms per kilomole? The same units as all of these molar masses? So this is our first answer for part A. Box it, color it, make it look pretty, call that answer to part A. So too many digits, just move it over a little bit. There's 4 digits. So for this mixture, if I have 1 kilomole of the mixture, then I'll have 34.81 kilograms. Makes sense? Now, the next thing it said was the mass fraction. So I need the mass fraction for this mixture. Well, the mass fraction is, for the nitrogen, is going to be this many kilograms of nitrogen per that many kilograms of the total mixture, true? Now I'm going to drag that down, so I'm going to put a dollar sign there so it fixes. F8 doesn't change. So I drag this down and I see that I can put it in percentages. So my mass fraction is 32% of nitrogen, 63.2% is CO2, and 4.6% is methane. Just as a check, do this. Do the sum of those. They better add up to 100%, and they do. Over here for the Y's, we could have made them look a little prettier and then double check that the sum of those is equal to 100% as well. The sum of the mole fractions has to be 100%. The sum of the mass fractions has to be 100%. So that's check. But this is the answer to part B. What were the mass fractions?
What was the question?
Let's jump back to the question. It said, determine the analysis in terms of mass fractions. So we were given the molar analysis of 40%, 50%, 10%. We want the mass fractions, some percent for those 3 components. Now, what about the partial pressure of each component?
If anyone has any homework to turn in, no.
You got it. Please give it to him right now, okay? He's leaving. If you have any homework. John, you're good? Very good. Thank you. All right. So now the partial pressure of each component. How are we going to calculate that partial pressure? Using Dalton's law, concept of partial pressures, and that the total pressure multiplied by Y is the partial pressure. So the partial pressure in kilopascal, we want to calculate that. Let me try this, kilo. I like to put the correct, sometimes I don't do it, but the kilo is lowercase k, true or false? The pascal is uppercase P followed by lowercase a, true? So that's the best way to do it. We need to know the total pressure. And what was the total pressure? 100 kPa? And might as well put the temperature. And the temperature was 300 Kelvin. Oops. Auto-correct or auto-finish. They tried to think, they thought it was kilopascal. So if I want to know the partial pressure of the nitrogen in this mixture, it's the total pressure times Y. True? So we'll just lock in C1 so it doesn't change, and then we'll drag this down. If I do a sum of all of these partial pressures, guess what it should be? Back to the total pressure, 100 kilopascal. So this is all box it, color it, and that's the answer to part C. True? Now, what was the last part? It said if I have so many kilomoles, it said, look, you're given N to be equal to 1.5 kilomoles of that gas mixture. What volume does it occupy? The volume it occupies in cubic meter. That's the question. So how would you solve for that? Use the ideal gas equation, which is N times R bar 8.314 times the temperature divided by the pressure. Does that give you the volume? And so the volume would be this many cubic meters. And box it, color it. There you go. Then the last question was not that so many N was given, but M is given. If the mass is a different problem now, then it says it's 10 kilograms. What is the volume occupied by 10 kilograms? Just use the other form on the mass basis. So the volume in units of meters cubed will be equal to the total mass times the gas constant, which is R bar divided by the molar mass of the gas. So R bar 8.314 divided by the molar mass of the gas mixture. Now multiply that by temperature and divide by the pressure. And the answer is right there. You could have said, well, that seems more convoluted than I like. Why don't I do this? Why don't I take and just calculate the number of moles that 10 kilograms gives me, right? Well, that'll be 10 kilograms divided by the molar mass of the mixture. So this is how many kilomoles 10 kilograms gives me. Then I'm just back to how I solved for this one right here, true? So that volume was equal to the number of moles times R bar 8.314 times the temperature divided by the pressure. And you kind of went in a circle, but you got the same answer, true? And get rid of the color here. No fill there. But this is just a check. So that was the answer to part D and the answer to part E. Does that help? Look doable? Let's come back to the here. So this problem started with the molar analysis, true? Well, what happens if they say the gravimetric analysis of the gas mixture is this, right? Kind of like you worked with your right hand, now you got to work with your left hand. You have to be ambidextrous. So if we change this problem up, it's really not that hard to do. What I'll do here is I'm just going to copy this spreadsheet, go to a clean spreadsheet, paste it, but I'm going to make reuse as much as possible. So we still have the molar masses didn't change, but instead of being Y, we're given those as our mass fractions. So it's a different problem, but it's 40%, 50%, 10% is mass fraction, true? So instead of thinking of starting with an assumption of the total number being 1 kilomole, start with the total mass being 1 kilogram, true? And so now I have 0.4 kilograms of nitrogen, 0.5 kilograms of CO2. If that's true, then how many kilomoles do I have? Well, I take the mass, and instead of multiplying by the molar mass, I divide by the molar mass. Won't that give me the number of moles? And so then you work your way down here. So we find that the total number of kilomoles is this. If you started with 1 kilogram of the mixture. So what is our new equation for the molar mass? Well, the molar mass of the mixture is how many kilograms. We started with the assumption of 1. and you have so many kilomoles, 0.0318, blah, 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 blah. So there's our molar mass of this new mixture. It's very close to the previous, but it's not exactly the same because we were given information on a mass basis, not a molar basis. Okay, so now what is Y? Our mole fractions. Isn't that equal to how many moles divided by the total number of moles? Is that true? So we find that it's 44, blah, 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 blah. And then it adds up back to 100%. So if we started with 40% mass fraction, the mole fraction is 44.8. So that's why. What about the partial pressure? Well, don't multiply by the mass fraction, multiply by the mole fraction, true? And drag down and clean up the units a little bit. But you notice still that the sum of the partial pressures is the total pressure, 100. They're not easy numbers, not, you know, they're fractions there. Let's do this. You have the total number of moles of 1.5, right, of this mixture. What is the volume? Is that the same volume? 1.5? Well, the same temperature, the same pressure, the same total number of moles. Yes, it is. 10 kilograms, true? Well, as long as I use the correct molar mass of the mixture, it works. And this is the same, and that's the same. So the rest of it works. So we reused quite a bit of this little spreadsheet, did we not? And we changed it around. You have to be able to go back and forth between mole fraction, mass fraction, and mole fraction. Look good? You're experts. That's good. Let's jump back to this. Amagat's model. Well, we had Dalton's law of partial pressures. There's another one of partial volumes. Some people would call it Amagat, some people not. But it assumes that each mixture component behaves as an ideal gas, as if it existed separately at the same pressure and temperature. So the volumes are different. So think about this. If I have my volume here, and it's made up of, I don't know, nitrogen and oxygen. Try to color code them so you can see. And I'm going to, in a thought experiment, split them into such that I have in one container only the red, but the container has to be at the same pressure and the same temperature as what it started at. So what's going to be different? The volume is going to be much less. And then another container, I'm showing it too big, let me make it smaller, which will be filled with the blue, and the blue is at the same pressure and the same temperature, but the volume will be less. And what we find is the total volume is equal to the sum of the partial volumes. So Dalton gave us a concept of partial pressures. Here's another one. It's a partial volume. All right. What's the use of this description? Well, let's try and work through this a little bit. But if I said that, recall from Dalton, one of the big things from Dalton's law is that the pressure of component I is equal to Y sub I times P total. Remember that? Okay. How about this one? The volume, the partial volume, is equal to Y sub I times V total. You can get the similar result here. You're just going to use the ideal gas equation. Okay. So let's do this. If I have, let me try and just reestablish this result right here. What is P VI is equal to N sub I R bar T? Does that make sense? And then we have also that PV total is equal to N total R bar T. True? So I take the first equation and divide it by PV. And on the right-hand side of the first equation, I divide it by NR bar T. So I divide it by this part, then that part. They're equal parts. So what we do is we can cancel the R bar T's, the pressures, and we find that Y sub I is equal to V sub I divided by V. Or rewrite it just like this. So what we have is the partial volume is equal to, or the volume fraction is equal to the mole fraction for ideal gases.